previous module we have been looking at thermal comfort in built environment. Primarily we talked about the basics of thermal comfort and factors influencing it. Now we will start looking at what comfort zone is, how do we define comfort zone, how comfort zone is defined in international models as well as Indian models. We will look at few examples. First let us take a look at how do we primarily define comfort zone. I am referring to ASHRAE standard 55 thermal comfort standard. This is a psychrometric chart. We have been talking about psychrometrics. You have, instead of, there is one small change in the psychrometric chart. Instead of dry bulb temperature, here we have something called operative temperature, which is equivalent to, say, in still air about less than 0.5 or say 0.2 meter per second air velocity, more or less still air. It is half of dry bulb temperature plus half of mean radiant temperature. This is replacing the dry bulb temperature in the actual psychrometric chart. Right hand axis you have humidity ratio, then you have these lines, relative humidity lines. Now comfort is defined based on, one is environmental condition, here temperatures and humidities. Apart from this, you also have the clothing insulation and metabolic activity, the personal variables. This comfort zone actually includes all these factors. There are two boxes, if you look at it closely. There is one shaded box which is ranging somewhere between 25 degrees operative temperature. It goes more close to 27.5 degrees operative temperature at very low humidity, and at high humidities it is around 24 to somewhere around 26.5 degrees here when the humidity increases. Beyond this the comfort zone does not extend, which means you will not have thermal comfort beyond this point. This is the international scale, we will come to applicability later, but quickly this is the comfort zone with 0.5 clo value. When your clothing insulation is 0.5, you have a light summer wear, then this would be your comfort zone. What happens when you put on slightly thicker cloths, winter cloth or thermal wear for instance, not to the extent of total blazer kind of a thing, you have say 1 clo value, which is not a total thermal wear, insulated thermal wear, but more or less like an office cloth, suits, office suits, you will have close to 1 clo value. Essentially what happens in the comfort zone, it starts moving towards your left side. So instead of the comfort starting from 25 degrees, it goes as low as 21.5 degrees. So if you are tightly dressed, if your thermal insulation, clothing thermal insulation is getting higher, you will need lower ambient temperatures for yourself to be comfortable. So from 0.5 clo value, the upper and lower limits have tilted or moved towards left side. Apart from this, when you are doing higher metabolic rate activity, you are, instead of sedentary activity, you are getting into more strenuous physical activity, then your comfort zone will move towards your left, apart from the clothing insulation. Then when you have a higher radiant temperature, MRT or globe temperature is getting higher, then your comfort zone will move towards your left. On the other hand, if your clothing insulation is further low, or your metabolic activity is getting further low, or the radiant temperature are lower comparatively, you have more colder surfaces around you, even when temperatures and conditions are not suitable, if these conditions prevail, your comfort zone would start moving towards your right, not to the farther extent, but there is a limit within which it can move. Another thing you can notice, this is with an air velocity of 0.1 meter per second, and when you have air velocities up to 1.2 meter per second, then your comfort zone can still be higher. If you take a closer look, say take a temperature, take a relative humidity of around 20% here, somewhere close to this, your lower limit of the actual comfort zone was around 24.5, 25 degrees, and the upper limit was somewhere close to 27 degrees. But this is at still air, around 0.1 meter per second, or when there is still air. When you have a higher air velocity, when your air velocities are above 1 meter per second, say 1.2 meter per second is what is given in the chart, then at the same relative humidity, the lower limit would be somewhere around 26 degrees operative temperature, and upper limit can be as high as 31.5 degrees. Even with 31.5 degrees operative temperature, you will still be within comfort zone when you have enough air velocity. This is a kind of comfort zone which is defined in ASHRAE. We will look at more models quickly. Coming to our Indian model, this is not a graphic representation, but they have nicely presented two tables. I am referring to Bureau of Indian Standard SP 41 special publication. This is Handbook of Functional Efficiency in Buildings. This is a very old standard which has been in use. Two nice tables have been presented here. Similar looking tables, but only difference is this is a set of conditions for comfort, thermal comfort, and the next table is conditions for acceptably warm conditions. It does not have to be really comfortable, but it can also be acceptably warm, but still I can accept it. Then the conditions slightly differ. First let us take a look at this first table. Here you have dry bulb temperatures starting from 28 to 35 degrees. On this, along the row you have relative humidity starting from 30% going all the way up to 90%. And what these numbers represent? They represent the required amount of air velocities. Say for instance, your air temperature is 30 degrees, your relative humidity is somewhere around 60%. It says 0.06, which means you may not need much of air movement to be comfortable. Even with at 30 degrees and 60% relative humidity, with still air you can still be comfortable. These tests were done for Indian subjects, so the derivations hold good for most of warm, humid, composite or hot dry regions of India. 30 degrees, 60% relative humidity, you will still be comfortable without air movement. Now if the relative humidity increases to 80%, same temperature 30 degrees, humidity increases to 80%, you will need 0.5 meter per second air velocity in order to be comfortable. Looking back at our measurement, we said with a well cross ventilated residential space, you will expect around 0.4 to 0.5 meter per second air velocity, which means temperature is 30 degrees, up to 80% humidity you will still be comfortable, and marginally you will be comfortable even at 90% relative humidity. But as the temperature increases, take a case of say 32 degrees here, when it is 50% humid you will already need 1 meter per second air velocity, and as you go up say 80%, you will almost need a very strong wind or 3 meter per second air velocity. When it further increases, this means you cannot attain comfort. Take a case of 35 degree temperature, 30% humidity, you will need 3 meter per second air velocity to be comfortable, but beyond that even a slight increase in relative humidity you cannot attain comfort. Similar table, the same you will find dry bulb in this along this column and relative humidity along this row, but the number changes considerably and the extent also increases. The earlier table we had up to 35 degrees, here we have another degree added up. This is acceptably warm condition. What they say, 30 degrees, 60% relative humidity, they say it is acceptable, it does not need any air velocity, this does not arise at all. Even 33 degrees, 40% relative humidity, without much of air movement you can still be comfortably warm. There is a term called acceptably warm, which means it is okay, you can accept it. 35 degrees, 40% humidity, you will need around 1.5 meter per second air velocity. Typically with a ceiling fan or a pedestal fan, table fan, you will be able to much closer around the vicinity of the throw, you will be able to get around 1 to sometimes 1.5 meter per second air velocity. If you are really close to a pedestal fan, you will be able to manage 1.5 meter per second air velocities. A typical example which we worked out, an interesting case is we know that these boundary conditions are existing. How do we really report? Say you want to measure for your own classroom or for your house and you have to report that whether temperature, humidity, air velocity is okay or not. A minimum climatology lab will have sensors for temperature, relative humidity as well as anemometer. With these quick handy things you can do simple experiments and you can report it this way as per you can say as per National Building Code whether comfort conditions or acceptably warm conditions are existing or not. A simple way of reporting. Here what we have done, we have taken the similar condition, indoor temperature, this we call crosstab statistics, simple analysis, temperatures here, relative humidity here, and this percentage represents how much percentage of data falls within this combination. Say we did not measure anything with 31 degrees and 20% humidity, whereas we had about 1.5% of data falling in 31 degree and 1.5 50% relative humidity. 34 degrees 50% relative humidity we had at about 7% data. Similarly if you look at this, about 28% of the data was around 34 degree. If you look at this way, around 29-30% of the data had 60% relative humidity. With this if you make a chart, simple chart, again this has a constant air velocity. we had a ceiling fan running, which means the air velocity is around 0.8 to 1 meter per second roughly, say around 0.8 meter per second. With that air velocity, these are the temperature and humidity combination, which means out of the whole thing 54%, 54.6% was comfortable, this whole area, 41.7% was tolerable, tolerably warm, then you have 4% which is uncomfortable. So this is how a simple example of how to consolidate your comfort reporting using simple instrumentation and day to day measurements. What are the other considerations apart from these 6 things which we talked about? Important factor is something called draught. Imagine it is a very cold day, you have a chill breeze coming through your window, then you feel the chill. Sometimes outdoor conditions we call it wind chill, you call it draught in the indoor cold air. Then you have vertical temperature difference, you are sitting next to a heater or an air conditioner, then the temperature difference between the foot as well as the head level considerably varies. So the vertical temperature difference, I am going to show you a few numbers where you can actually determine what is the percentage of discomfort as well. Apart from this, you have something called radiant asymmetry. I showed you a sensor using which we can measure radiant asymmetry. You are sitting in the center of the room, one side you have a hot surface, say a large glazed window where you have direct solar radiation. So this particular surface is hot, you have radiant heat gain from one surface, the other surface is really cold, so you have heat losses happening, radiant heat losses happening to the other surface. Then you are starting to experience something called radiant thermal asymmetry. This can also happen in the vertical plane. You are on the topmost floor of a building, your roof starts radiating lot of heat, your floor is not that hot, so there is a kind of radiant asymmetry which is existing. Or you have underfloor air conditioning system, you get the chill surfaces in the bottom plus the ceiling is emitting, the roof is emitting lot of heat, you have radiant asymmetry along the vertical axis. Then you have floor temperature differences, this is primarily due to conductive heat flow, this also has a major concern in terms of comfort apart from these 6 parameters which we were talking about earlier. Take a more closer look at radiant asymmetry. Like I said, on a colder day you are sitting next to a window, one side is really cold, this window surface temperatures are getting as close to single digit numbers, say 4 to 5 degrees you get in the window surface. The indoor environment is heated, so more or less the surface temperatures are revolving around 20-21 degrees. So you clearly get around 15 to 18 degrees temperature difference between this surface and this surface. So when you do the same mean radiant temperature calculation which I was talking to you about, then the emission from this surface versus the absorption towards this surface is going to be considerably different. These standards where I am referring to, ISO 7730 gives you a simple graphic indicator of what is a delta T, that is a temperature difference between one side to the other side, and with the increase of this how much will be the increase in percentage of people who are going to be dissatisfied. It varies from person to person, so typically we express in terms of percentage of people who are dissatisfied with it. So the dissatisfaction goes up as this temperature difference increases. This also varies for a warm ceiling, the same example I was talking to you about, an exposed roof case versus a cold floor surface, the vertical difference, or a cold ceiling, say when you have snow on the roof surface, your surface is going to be cold on top, the floor is heated now. This difference, this is also considerably different from one warm ceiling is different from that of a cold ceiling, cold wall is different from that of the warm wall, the percentage of dissatisfied and the pattern of variation is also going to vary. Then the vertical temperature differences, I am going to shortly show you some examples of what we actually measured. Vertical temperature difference occurs both in air conditioned as well as unair conditioned, non-air conditioned or so called free running spaces. As the vertical temperature difference increases, then your percentage PD, percentage of dissatisfied increases. It is not so linear, but still it increases with it is directly proportional. As this increases, this will also increase. Typically in air conditioned spaces, cold air settles down, the warm air rises up, so naturally you will have a vertical temperature stratification or difference. So you can easily find about 3.5 to 4 degrees vertical temperature difference, but it depends on the floor to ceiling height, how much height it is. Say if it is 3 meters, the difference might be slightly lower, but if you are talking about a 5 meter or 6 meter tall space, then the vertical temperature difference is going to be considerably different. But even in the case of naturally ventilated space, here we took measurement in a naturally ventilated building. This is again a hot and humid climate. We took measurements at 3 different heights, 0.1 meter height which corresponds to the foot level of a standing person, 1.6 meter height, this is somewhere in the center of the room or which corresponds to your face or head level, 2.9 meter height which is much close to the ceiling. The roof is exposed. So, what kind of difference you find here? The maximum difference is 33.5 to 36.5 which is about 3 degrees difference, the peak level, but eventually it comes down. Even when it is low, the minimum difference you get is also around 1.5 degrees. So, vertical temperature difference considerably varies, but one thing you need to note here, these two lines, this blue and green line, that is the foot level and the 1.6 meter, that is the head level. This is considerably different, but at one point they converge and then this particular level 1.6 meter drops down below the 0.1 meter line here. This is the temperature at the floor level, this is the temperature at the head level. This was interesting because what we noted, as the convective mechanism sets up, the heat is dissipated, this is also lying in the window plane, it is cross ventilated. So, the temperature eventually drops down, there is not much of difference, around 0.5 degrees, but still this drops down while the floor level temperature more or less was stale and it was revolving around 33 degrees. Even after that it does not fall much below 32 degrees. It also depends slightly on the material used. The earlier was solid cement block, this is like a low density block, it can be an aerated concrete or a hollow wall, a cavity wall system. Even there you will find the vertical temperature difference, it will considerably be different from one material to other, the magnitude may be different but the pattern of variation remains the same. We were talking about other phenomena, the drought, external environment we call it wind chill. There are different indices, the commonly used is wind chill index. What this tells you, below freezing point as the temperature goes further and further, and if the wind velocities are increasing, the same amount of temperature, the same 20 degrees which you perceive at 2 meter per second air velocity versus the same 20 degree you face at 20 meter per second air velocity, you will start feeling very cold, there is a danger of frostbite and there is a real danger of casualties because of frostbite. On the other hand, with respect to hotter environments, you have the heat stress, there are indices like heat stress index, wet bulb globe temperature WBGT, these are heat stress indices which combine air temperature as well as humidity. As the temperature increases and as the humidity also goes up, the amount of heat stress increases, the WBGT or heat stress index might go up. There are different indicators, this is just to give you a simple example. Let us quickly take a look at 2-3 comfort models and how they work around. I have presented a list of comfort models, not an exhaustive list but a few commonly referred models starting from wet bulb temperature, it goes on to tropical summer index, this is one of the index developed in India. These are different environmental and personal variables. TI is dry bulb temperature, globe temperature, air velocity, this is vapor pressure, relative humidity, this is operative temperature. Then you have metabolic activity and the clothing insulation, 2 personal variables. Just to give you an idea about what are the parameters these indices actually take into consideration. If you take an index like wet bulb temperature, it takes air temperature as well as relative humidity into consideration. You take an index like heat stress index, it takes indoor dry bulb temperature, globe temperature as well as WTW wet bulb temperature into account. Then you have something like predicted mean vote, we will look at it shortly. This is a comfort model, this takes into account globe temperature, vapor pressure, operative temperature as well as 2 personal variables which is metabolic activity and clothing insulation. You take the Indian index, this is KSU Kansas State University TSV thermal sensation vote, these are different indicators, you will also find effective temperature, standard and corrected effective temperatures here. Tropical summer index again includes globe temperature, air velocity, it includes wet bulb temperature which is further a factor of air temperature and relative humidity or vapor pressure, but it does not include metabolic and clothing insulation. No personal variables are associated but environmental parameters are taken into consideration. Among the international models, there are a lot of international models, among them 2 commonly used or most often revised and revisited models include the 2-node model, commonly called as 2-node model, which is developed by the Pierce laboratory, JB Pierce laboratory. and next is the Fanger's comfort equation. Apart from this, you also have models like Munich energy model. There are a lot of models, but apart from this, these are two most commonly used models, and of course the Indian model developed in CBRI Roorkee way back in the 80s, 70s and 80s. This is a tropical summer index. We will look at two of these models more closely. First is the two node model, the Peirce's two node model. This works on the metabolic heat exchange or the thermal equilibrium between the body and the environment. This takes two nodes, first is the core body temperature, then is the surface temperature, and then the ambience. So this actually calculates how much is the heat exchange between the core body and the skin, and then how much is the exchange, effective exchange between the skin and the ambient condition. It can be indoor or outdoor condition. So effectively it summarizes, it also includes the effect of clothing and the metabolic activity, because you are talking about the metabolic heat generation. So it is typically a heat transfer model where thermal equilibrium is obtained. You call it is thermal, it is not actually thermal comfort, but it is thermal equilibrium. That is what this model tries to derive. The next commonly used model, or most familiar model rather, is the Fanger's PMV model. Fanger is a scientist who developed this model. This is predicted mean vote. So as the name says, it is a kind of predictive index. The basic theory behind, or the philosophy behind it is, he pulled in more than 100 people, he pulled them in a laboratory, he varied the environmental parameters, 4 environmental parameters: temperature, humidity, air velocity and radiation, as well as 2 personal variables, metabolic activity. He made them do different activities, plus he asked them to vary the clothing insulation. With these variations, parametrically he determined what is the comfort vote for each of these set of conditions. So based on this, he also determined another indicator called predicted percentage dissatisfied. At certain kind of environmental condition and personal variable combinations, how many percentage of, how much percentage of people are really feeling uncomfortable. So this is an inverse bell shaped curve. It is a double Likert scale. It starts from 0, which is neutral. On the other, one side, right hand side, it has slightly warm, which is +1, indicated as number +1, warm and hot. On the other side, it goes to -1, -2 and -3. This is cold. Some cases, if you are doing in extreme conditions, say if you are evaluating PMV in India, it may go to -3.5, -4, because we are dealing with more hotter conditions. We will look at it, but typically the actual scale given is +3 to -3. Both ISO 7730 thermal comfort standard as well as ASHRAE 55 standard refer to Fanger's model. There has been lot of modifications to Fanger's model as well, but primarily this is an inverse bell shaped curve. What we need to note, when there is 0, which means thermal neutrality, we talked about thermal equilibrium and neutrality. When there is thermal neutrality, this is at its minimum, that is percentage of people dissatisfied is at the minimum, but still it is around 5%, which indicates even with ideal condition, when all the environmental variables as well as personal variables are more or less amicable, still there will be about 5% of people, say 5 out of 100 would still be feeling uncomfortable. Leaving them aside, this particular curve will increase if your predicted mean vote increases, say from 0 to 1, 1 to 2 or 2 to 3, there will be an increase. At around 2, the percentage of people dissatisfied will be 80%, and further it will go up. And similarly on the negative side, that is on the colder side also. But one quick thing, a note we have to take, we will look more about it in the adaptive comfort section, the further following module. But one quick thing we have to observe here is, as stated, these are results based on standard static laboratory conditions. There are set of environmental variables which are preset, and people are responding to these environmental variables. They were not allowed to get adjusted or acclimatized to these things. They were not adjusted, allowed to adjust their clothing insulation, nor adjust their movement or any kind of parameter, temperature, humidity, radiation, nothing. They didn't have any personalized controls available. So there is a lot of debate going on about whether the Fanger's PME model really applies to the field or not. There has been a lot of investigations which say that it needs a correction with which it can apply to the field. Some of the authors also cite that this is far beyond field application, this is more lab oriented index, but all said and done, this is a parametric equation, or rather an empirical equation which based on which the PMV is derived. It has variables from metabolic activity, it has variables like the clothing, surface factor of clothing, radiant temperature is there, then heat transfer coefficient, air temperature is available. So doing this, it is an exponential empirical equation based on which you will be able to predict PMV. Moment you know PMV, similar fashion you can also determine PPD. It is a kind of extended heat balance equation in which both environmental as well as personal variables are taken into account. Even with corrections, we have found that some of the field studies, through field studies, this model applies well and it is more or less a balanced kind of an approach to predict environmental conditions. Some of the measurements for your reference, I am not getting into details much of what this is. This is outdoor air temperature and this is PMV. The left hand y axis is PMV. This is air temperature taken in Bangalore. How it varies during summer? Summer in Bangalore, PMV varies around 1. This is in the case of Hyderabad as well as Chennai. It goes, as I said, it can go up to 3.54 sometimes. It depends primarily on temperature, humidities. As such, this is developed for European subjects. So the applicability in Indian context is not directly, but you have to apply certain weightage factors, you have to do field validations before applying this parameter. In case of Ahmedabad, hot and dry climate, during summer, this is a comfort band -1 to +1 typically. If you say just 20% of people dissatisfied is permissible, during winter it goes below, that is touches -1.5, but summer it goes around 3.5, whereas a place like humid region like warm and humid climate like Chennai, during summer it touches around 1, close to 1.5, but in summer it goes beyond 3, it touches sometime around 3.5, 3.8. Does not mean it is unbearably hot, people can still accept it, but as I said, this model will really need validation for application in actual field conditions. As such, you can also find differences in terms of building exposure. PMV will show certain difference because MRT, or radiant temperature, is part of the PMV equation. So the effect of orientation will have an impact on PMV. Finally, the tropical summer index, or which is the index which is developed in the Indian context with Indian subjects. The tests were more or less like the PMV model. Again, people were asked to choose which conditions, environmental conditions they are comfortable with. Based on this, an index or the boundary limits of comfort was actually tuned. These experiments were done around 1980s, 75 to 80 these experiments were done, but this does not include personal variables like PMV. This excludes metabolic activity and clothing insulation, but it takes into account wet bulb temperature, globe temperature and air velocity. So if you closely look at the equation, globe temperature has a maximum weightage, this has 0.75 of globe temperature, which means an increase of globe temperature will have the maximum impact on tropical summer index, whereas an increase of wet bulb temperature, say humidity goes up high, wet bulb temperature is affected, it has about 0.31, which means around 30% or less impact. This will have, compared to globe temperature, the impact of wet bulb temperature is lesser, but both of these things will result in increase of tropical summer index, while air velocity is in negative. If you want to improve thermal comfort, you provide more air velocity, say simple enhancing cross ventilation, turning on a ceiling fan or a pedestal fan, you improve or increase the air velocity, because of which you are able to reduce tropical summer index. Say take an air velocity of 1 meter per second, you will reduce the tropical summer index almost by 2 degrees. On the psychrometric chart, same, this has a dry bulb temperature, vapor pressure, relative humidity lines are there. Tropical index, tropical summer index has the boundary of comfort drawn somewhere here. So below 30% relative humidity it is not comfortable, and above 70% relative humidity it is not comfortable. If you take a closer look at it, it starts somewhere from 28 degrees, 30% relative humidity, 27 degrees, and then on the farther end, when the humidities are also high, it tilts towards the left. You can be comfortable up to 70% humidity and around 29 degrees temperature. When the humidities are lower, say 30% humidity, you can be comfortable up to 31 degrees. Like we saw in Fanger's index, there we had percentage people dissatisfied, here it is percentage people comfortable, it is a bell shaped curve. As the tropical summer index drops, that is it goes towards the lower temperature side, the number of people feeling comfortable drops down. Similarly, when the temperatures goes up, the number of people feeling comfortable also drops down. So typically we define comfort in this way. Again, if you have to really improve on this index, you have to include the effect of air metabolic activity and clothing insulation. The effect of cross ventilation, like I said, it can easily bring down to 2.5 degrees in terms of tropical summer index. So, we will close this session here. To get a recap, we looked at the comfort zone, how comfort zone is defined in international models. We looked at the ASHRAE comfort zone, then we looked at how Indian standard defines comfort zone. Then we also looked at certain comfort models. Primarily we looked at the Pearson's 2-node model and Fanger's comfort model, apart from which we also looked at the tropical summer index, which is in the applicable more in the Indian context. Thank you.